Good morning. This is the 29th of April and the last of the videos that I'm going to be presenting this semester. And we want to talk a little bit about Chapter 10. This is a review, and we basically are in this chapter talking about things that are not necessarily programming in nature, but they're outside. The focus this chapter is things outside of the control panel, things that you must consider in addition to building a control panel and programming your process. So this is just a group of things that you must think about as you are setting up your control scheme and what you're going to do. And it's not complete in the sense that this is everything, but it shows you the breadth. This chapter shows you the breadth of the things that you're supposed to consider when you're doing a controls job. And one of the things that you're going to have to do is sensors. And a lot of the things that we talk about in this chapter start with the letter S. And I thought about at one time just saying that the chapter was everything that begins with the letter S, but then we added analog and troubleshooting, and we kind of got away from that, but we basically do have a bunch of stuff that some of it starts with the letter S and some of it doesn't. But anyway, the first one is sensors. And the sensors that we're going to talk about here are the breadth of things you're going to find in a factory. The type of sensors that you're going to find in a factory typically are at a higher level and are more robust than what you would use for a kit that you would use for a toy robot or something like that. If you're buying something that you're going to attach to an Arduino, typically those sensors are not what you would find in a factory, but they can be. Sometimes if you don't need high accuracy, or if you don't need the guarantee that it's going to work all the time, people do use devices from things like Arduinos, but typically they don't. And typically the instrumentation that you buy and the sensors that you buy are more robust, and they have to take a hit and basically be able to perform. So that said, there's a lot of different types, and I just list a couple here, a few, and I give you the idea that there's a lot more than this. If you are involved in selecting those sensors, wish you the best. There's a lot, and there's a lot to do here, and a lot of things to try as you are going forward with sensors. Obviously, they're the first thing. They're the eyes of your project or your process, and they are something that you're going to have to check out. Each sensor has some input sensing capability that's going to send you a program, send signals to your program, and they're going to have to be set up. There's no way that you can start your program up without having checked to see if the sensor is working and working correctly. Any sensor that you leave, just say, well, I hope that it works, it won't work. So you're going to have to go through each of the sensors and test them, both for is it on, is it off, that type of thing. You're going to have to do that as you start your checkout of your project. And once you start looking at sensors, if you're selecting sensors, you'll find there's a great grade of types. There's different types, there's different grades within each type, and you're going to have to do a lot of work if you're responsible for selecting sensors. Many of you will not be selecting a lot of sensors. Mostly the mechanical people will be selecting the sensors, but you might, and if you are, there's a lot. And this just gives you some of the various types, and for each type there's various ones. One of the ones that you're going to use a lot of are photo eyes, and the sensor that is in your garage, or many of your garages, that transmits a signal across and will stop the garage door from coming down. If there's a car partially in the garage blocking the signal, that it basically is a photo eye, and it transmits a signal, and then there is a reflector, and it comes back, and you have a receiver as well, or some of them have the transmitter on one side and the receiver on the other. Either way, they work the same. Now, at one time, photo eyes were not very accurate, and or they were not very reliable. They were accurate to sense light, but they sensed any kind of light. And if you had ambient light, they would sense that. So what they did was they took an electronic circuit and they built a pulsar circuit, and that pulsed a light emitting diode of a certain wavelength, and that pulse and that certain wavelength became what the receiver would accept. Any other pulse length or any other light wavelength would not be accepted. So they basically changed it from any source of light to a very specific source of light, and that changed the dynamics of photo eyes. And photo eyes from that point on have become very commonplace and very reliable. And they're very, as far as expense is concerned, they're one of the least expensive circuits that you can buy. Photo eyes and proximity switches are two of the cheapest for sensing of a product, absence or presence of a product on a line or in an area. So basically they're very, 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 very useful. And the Banner Engineering Corporation has a website, and they have an applications book that is very good, and I did use some of their examples to list some of the various types of photo eyes. And what you may or may not be impressed with is the number of different types of photo eyes. From that simple pulsing signal, they have a bunch of different ways of doing that. And let me just say that from past times that I've discussed this with you, there are salesmen who are interested in selling you these products, and they will have a bag of tricks, a suitcase full of the various types of photo eyes, and they can bring that suitcase of product into your facility and test which one would be the best. So you have to ask questions like, if there's a background, something that could trip this from the background, is there a speed issue? Is there an issue of conflicting signals and that type of thing? So you have to be willing to try various types in order to see which one is the best one. And as you go through this, you will find that there are ones that do the job for each application better than the others. And the people that are doing this, are bringing these things in, they're trained to suggest certain things, but you have to try them as well. So it's your job, because you're going to have to make this project work, to figure out which one's the best one. They're going to try to sell you their type, obviously, but which one of those types is up to you. But they're going to try to help you, and with that, they're going to try to get you so that you'll buy from them. That said, most of the various makers basically make all these types, so you can still go back and say, well, I'm going to still have to bid this or whatever, but it's up to you. But there's a lot of different types of photo eyes, and you are responsible for picking the one that is the best for you. And I go through some of them and the various modes, and you're going to see some of these that are some are better for certain applications and some are better for others. And I'm not going to worry about them today, but you're going to have to, at some point in time, probably pick which one was the best one for your application. There's a sensing range and an envelope of how far out you can go. And as you notice, most of these, there's a wide envelope that they can go out. So you have to be careful as to how you put these together. Okay. So we're going to move on from that. Now, if you wonder, is this a very big topic or is this a small topic? There's a lot of very big topics that are being covered here, and you might think that it's not as important because we only use a half a page, or we only use a page to cover a topic. These are all important topics. They all have a great value, but we just don't have enough to get into each of these areas and talk about them extensively. You might become, in your organization, the machine vision expert. This is a whole area of expertise that you might learn and become very, very proficient in. And so the idea of cameras and looking at parts and inspecting parts, or maybe a combination of a machine vision and a robotic, but either used in conjunction with robotics or just as inspection stations by themselves. The machine vision is a very big topic, and we only cover it very, very lightly. But that being said, you may end up becoming an expert in this area and spending a lot of time studying machine vision. Also, the idea of reading a barcode or an RFID tag. So each of these methods can be useful for identifying what a box or a piece of equipment is. A barcode cannot be modified. An RFID tag, on the other hand, you can write to as well as read. So with a barcode, you've seen these on products in the grocery store, etc., etc. And you can also have these on various devices and various things in a factory. If you put a barcode on a product, then you can read it, and then you can reprint the label, and you can do all kinds of stuff with it. Likewise, with a RFID tag, you can do the same thing. You can go up to it and you can read it, and here is an example of an RFID tag. Now, this has memory on it, and the reader can actually, if it gets close to this tag, can actually read the information off that tag. And there's, you can get them in 2K, 5K, 10K. This is 32K of RAM. So you can have a lot of data stored on these little disks. A cow, a livestock, will have an RFID tag. It's not a read-write tag, it's a read-only tag, but they place those in their ear, and they put those in their ear when they're newly born, and then that tag, it's a 20-character tag, is read each time that calf or cow is dealt with. In other words, you do something to it, you give it a shot, you check it out, you weigh it, all those things you record based on that RFID tag that's in its ear. So there's a wand that you would carry, and you would have the wand, and you would go up to it and wand the ear, and then weigh it, wand the ear, and then give it a shot, wand the ear, and then do something else. But basically, that's how you keep track of animals too. This is a device that can be used to keep track of animals, and these are useful in all kinds of applications, and these can be read to and written to as well. Okay, now how you design equipment is very important. You have to have safe equipment. You have to be safe so that the operator is not hurt, nor is anybody else in the plant hurt. So you're protecting the people in the plant. And the Machine Directive basically is, we'll discuss here, but it's basically an idea of how to make sure that machinery is kept safe. This is a picture of a plant that caught on fire in China last year, and it was a pesticide plant in Jiangsu province, March 21st, 2019. So there is an example of something that you would not want to have happen, and this is not good. And obviously it leads to lawsuits and loss of income and plants being shut down. But more than that, if you're the engineer who designed it, it's on you as well. So you have to be very careful how you design things so that they don't kill people, okay, or cause problems with the people in the area or in the operators. So again, not to scare you, but just that you are responsible for designing of machinery that goes into these plants, and that's what you're going to be asked to do, is to make it safe. Okay, so the standard in the United States is NFPA 79, and this is a review of some of those things that are in it, and some of the things that are in it are tell you how to build guards and stuff like that, and it refers you to other standards as well. And there's a robotic standard, there's other standards as well, but they start from this NFPA 79. One of the things you're going to be asked to do is to become familiar with and to do what we call a risk assessment. We're going to talk about risk assessment here in a minute. There's two types basically of protecting people. There's the fail-safe and there's the fault-tolerant. Now that plant that blew up in China, there was something there about fault-tolerant. You could also say, okay, if you have somebody that loses an arm or they impaled by a robot or something like that, that's fail-safe. Both of these are problems that you have to deal with. You say, well, I'm only going to deal with this type. I can't worry about this type. No, you got to worry about both. In some applications, this type dominates. In other applications, this type dominates. But you have to be careful because either or both are present in many facilities. So you have to be able to do whatever it is. In a fail-safe application, you have to guarantee that somebody is not going to be hurt. They're not going to be impaled by a robot, or they're not going to be an arm cut off or an eye gouged out or that type of thing. In a fault tolerant, you're going to have to guarantee that things do not blow up. There's no imminent doom as far as the process going out of control. So they both have safety issues that you have to be careful and address. And some of these are, this one is for the guarding of machinery, and there's different for both US and Europe, and we also have for the fault tolerant. So when you do a risk assessment, what do you do? Well, before you design your system, you go through a process, and this is called a risk assessment. And you look at a process and you look at an area and you estimate, is it acceptable? And if you say yes, you go on to the next one. If you say no, you have to mitigate. You have to do something that mitigates that. And you keep doing this process until you go this way. So you say, well, I want to put in this, or I'm going to put in that, and this process has to be documented. You have to do this, and you have to report it, all that kind of stuff. Now in Europe, a lot of this stuff is pre-done for you, and the people that do that is the German corporation. It used to be called BGIA. They've changed their name, but if you were to Google BGIA, you would get the risk assessment information from the this is a German insurance company directive, and basically what they've done is they've gone through and they've evaluated each of the basic movements or actions that you could do, and they basically give you a method for making it so that it's safe. So they give you a standard way of doing various things, and you can look at their reports and you can say, well, this would work in this area, this would work in that area, so I'm going to do this here and I'm going to do that there. So they basically have done your work for you. If you can find the actual application of what you're doing, then you can use their evaluations instead of having to come up with this yourself. So BGIA is the German word of doing it. Now, here's another one. There is a thing called intrinsic safety. So when you do have something that can blow up, like petroleum, like grain dust, there are certain things that you have to do up front, and that is called intrinsic safety. Now, this is not necessarily, this accident here was not intrinsic safety related, but anytime you have grain handling facilities, you have the idea of grain dust, which can in fact blow up. But this one had to do with a person getting trapped, two people getting suffocated. But just to let you know that anytime you have grain handling facilities, you have to abide by the intrinsic safety rules. And where are they found? Well, they're found in NFPA, or the National Electric Code, on 500, 501, and 502. So the National Electric Code is where you would look. And also the Europeans have a directive called IEC EN 60079-10. So if you're dealing with things that can blow up, either grain dust, organic dusts or liquids like petroleum, any of those, you must read through and abide by the directives in National Electric Code sections 500, 501, and 502. Here is just a reminder that you have another area called burner management, and burner management is regulated as well. Most of the times you will just interface with somebody who is telling you what they want to have done, but you also may, with safety PLCs involved now, you might be able to incorporate these into the PLC. So NFPA 85 defines burner management in the United States, and IEC 61511 defines it in Europe. So what are we talking about? We're talking about a flame, and we're talking about natural gas, usually, and opening up a valve and letting gas in and letting in air, and then getting heat from that process. So anytime you have a boiler or an oven or a furnace, you have to have burner management control. And that's, like I said, it's all under these standards. Now we're going to talk a little bit about how the various program controllers get analog signals in. We've not talked a lot about analog signals, and yet they're a big part of the process that we have. They're a big part of any process, and you have to have the ability to get analog signals in and out of your program controller. Well, how is that done? Well, typically it's done through a method we would refer to as y equals mx plus b, which is basically you linearize the signal and you bring it in based on a minimum value and a maximum value. This all talks about that type of thing. How does Siemens do that specifically? Well, Siemens has two instructions called norm and scale. And these two instructions do that for you. So inside your program, to get a value to something that you can use, you do these two things, and then that analog value is workable in your range. Normalization takes it from the range that you have to a number between 0 and 1. The scaling value takes that number from 0 to 1 and puts it to the final scale that you want. So you use these two instructions, and then you use the output of the scale as the normalized value that you want for your signal to use in your program. So you bring it in raw, you do these two, and now it goes. So this is handled inside the program for Siemens. Allen Bradley does not do it that way. They basically take the signals that you have, you're bringing them in, and they do the configuration as you set up the card. So as you're setting up the card, you're actually linearizing these signals. So here you have a card you're bringing in, and you give a value, a name, and you give it a set point, low and high. And you do that through these signals. Right here it is. And you do this input configuration, you check what kind of coming in and scale for PID, and then you have a value that you actually can use, and you can scale it, and then you actually can use it in your program. Okay, so this gives you the ability to set up your input and your output information and use it in your program. Now, the ability to do this inside the MicroLogix is less than your ability to do this well in the ControlLogix platform. So if you're looking at a MicroLogix processor versus a ControlLogix processor, they do this more thoroughly in the ControlLogix processor than they do in the MicroLogix processor. So they do it kind of here for the MicroLogix, or the compact Logix, but for the compact, it's kind of skinny. The ControlLogix, it's much more thorough, and they do a much better job of getting that signal in a scaled value using ControlLogix processing. Okay, so basically Siemens uses two instructions, norm and scale, and with Allen Bradley you scale the value in the input tables that you're bringing the values in. So that's the two different ways of getting an analog value in or out of a processor. Now we have an area here called troubleshooting, and I have some information from Siemens especially on troubleshooting. They're similar to Allen Bradley. There's not a lot that you can't do either way, but realize that there are screens that you have that can help you with troubleshooting, online troubleshooting of your program. If you're having problems, there are some screens here that might be able to help you. The idea is that there's helps that you can utilize that will give you diagnostic status of your program and your program controller. Will show you some of the things that are going on. I have not used these a lot. I do recommend that you at least know that they exist. You need to know how much memory you've used, how to reset memory, that type of thing. But you'll figure these out as you go along, basically. And Allen Bradley has similar. It's not that one is better than the other. They're both basically the same. Here's the setting of the time of day clock. So we talked about time of day clocks before. Here's how it's set. Now, one of the best things that I could tell you about troubleshooting is this offline and online comparison. Realize that you do modifications when you're doing your programming. Realize that those changes to your program have maybe not been updated in your offline program. So you have an offline version and an online version, and as you go along, there is more of that. So basically, if these little bubbles here, these little circles, are orange, that means that there's a difference. So my suggestion to you is that you occasionally do an upload to your program controller and then a save and then maybe a download, or maybe just a download. But one of those may fix this. And I really believe strongly that if you have orange here, what am I looking at? What am I seeing? I don't know. But if I have green here, I know that what I'm seeing on the screen is the same as what's in the program controller and as what's in the offline program. That's very important to me, that I keep these as much green as I can. I realize you can't do it all the time, but many times that's how you fix problems, is to you make a change in the online and you don't get it in the offline and you forget about it and then you go on to something else and then you don't do an upload or a download and then you've got a mess. So my suggestion is to, as much as possible, keep these little guys green here, and then you're being careful that your offline and your online program are the same. Okay. Now they go through a watch table. We've already talked about watch tables in our course. It's not anything new, but this is something that if you've not used the watch table before, you should at least read it. It's a good place to start. Talk about glasses. Again, they're there. Okay. Some of this is pretty new, and this can be something that you can save a variable, and when you come back, when you're restarting your program, it brings a value back to a certain variable. You want to be careful how you do this, but at least you know that this capability exists. Forcing is something that we don't do a lot of, but you can. Both Allen Bradley and Siemens do allow you to force an output or an input. Just be aware of the fact that once you're done and once you're leaving and you're going on to something else, that you owe it to the people that you're setting your program up for, that you take all your forces out, that you do not leave a program with about a half a dozen forced issue IO. It will not work, and people they'll be very upset if you leave a bunch of forces in your program before you leave. Here is what we call a permissive string. So it takes all these things to turn on this relay. So any one of those can turn this thing off. Any one of those can knock off that burner. That's maybe a burner safety lineup. And any one of these things can cause that problem to exist. So what would you ask? What would be the question? Well, the question is, which one did it? And that way you would know which one actually was the problem. So basically, you are going to have someday in your life to write a first out. And this is a first out issue. Which one was the one that turned off, that turned this relay off? In other words, which one of these activated the first one to activate so that this thing turned off? This is similar to a programming like for the Jeopardy push button. Who pushed the button first? That type of thing. It's the same way here. Maybe you'd also want to know who pushed it second. But again, this is something I'm going to leave up to you, but you can add that as a programming step because you're going to have to do this. Here, we're talking about dangers of how do you put together systems that may or may not work. And here is a proximity switch. This is simple for a proximity switch. It's a 2-wire device that was meant to replace a 2-wire limit switch. But inside this is electronics. So when you turn off electronics, you turn it back on again, it takes a while for it to turn on and start working again. So when you do something like this push button, you basically said, I'm not going to let this thing work until it's warmed up. So this could be pushed, but this could not be on or not be responsible for at least 2 or 3/10 of a second. So it takes a while. So would you ever do something like this? Probably would not want to do that. This is something that, because this is an isolated output, in other words, you cannot get power down here without that pushing that button. This is not going to work for a while, and that may be enough time to slow you down or make something that not work the way you want it to work. So that's this one. Now this one is a little different because what I mentioned before is it borrows a little power. What it borrows is about 7 volts. So if you start with 110 volts, and this can only read on if you have 90 volts, this steals 7 volts, this steals 7 volts, this steals 7 volts. All of a sudden you're maybe right on the edge or maybe below the threshold for being able to read this as an on. So this is something you wouldn't want to do as well. You would probably want to just have one individual proximity switch hooked to one input. If somebody tells you you must do something like this, you want to question them because 2 probably would work, 3 will not work. Here is a checking of a switch or something that you might have, like a valve, and you might only need to know whether it's high, or you might say, I want to know when it's not high. But do you want to take this to an input and to take this to an input? Well, it may be that you don't really want to, but on the other hand, you probably should, because this gives you positive feedback that the switch is working and that the wiring is working. So you always want to check to see all states. Is it in the one position? Is it in the other position? Is it in neither position? Or is it in an invalid position? In other words, something happened here. This is not valid. You cannot have this state, and this would cause you to say, whoa, I got a problem. So that would be called pair monitoring. That's a type of diagnostic that you would want to have. Another type of diagnostic that you would want to have would be time monitoring. How long does it take to do something? You want to always put timers in for that type of application. So here's some examples of types of diagnostics that you would want to do in your program to make sure that things are working and working correctly. Here's something that I put in here. This is the old way of doing one-shots. So as you're looking at one-shots, you say, well, how did they used to do it? This is how they used to do it. Before we had a one-shot, this was the way it was done. Which leads to another subject, which is, this is one of them, and this would be another one. How do you get this? Well, you use this, the second bit of this one, as the input to this one. Use the second bit of that one to the input of this one. You lose the second one of that one to the input of this one. This gives me a 4-scan control of a specific action. You say, well, why would we ever do this? Well, if you're doing something on that is extremely time sensitive and it takes a lot of time to do this, you may want to split it up into multiple scans. In other words, you would say on the first scan I do part of the programming effort, some of it on the second, some of it on the third, and some of it on the fourth, and then at the end of this one I would actually report that out. So you're keeping your scan rate fast, and you're splitting up your execution of your program into multiple scans. This is something that you probably will do it from time to time because if you need speed. This is called a Johnson controller, which is the same thing as above, but it's on a continuing basis. And there's a way of programming a Johnson controller, although you have multiple ways of controlling a Johnson controller. Okay, so this chapter we're coming to an end. There's the summary, some exercises for you to look at. And again, Machine Directive and continuous process and fail-safe and fault tolerant for that one. At the end of this, we have a nice lab on multiplexers, which you have already done. Some of you have already done. And then also the bike, which is another project that you could work on in the end of this chapter, and it has analog input in it. And the analog input that's coming from this is what? Well, the first analog input is the voltage, and the voltage that's coming in is from a signal that goes from 0 to 12 volts. 12 volts is higher than 10 volts, so we have to do something to get it down to less than 10 volts. So we go through a voltage to current converter. This voltage converter goes to 24 volts input, and that converts into a current signal as an output. Well, how do you get 0 to 10 volts out of a current source? You put it across a resistor, and then you measure the voltage across the resistor. 470 ohm resistor, you can measure the voltage across that and get your input to your value. Okay. Also, how do you get the voltage of current? How do you measure current? We put in what we call a short stub or a shunt here, a resistor that's a shunt. It's a 0.02 resistor. So you measure the voltage on this side, you measure the voltage on this side. The difference is the voltage drop across that 0.02 ohm resistor. And that is enough that you can read that you can get the current off of it. And that gives you the current. How do you get the power? Because this is in phase, V equals IR, or excuse me, P equals V times I, this value times this value, and away you go. And that's how you get watts. Joules and calories leave you how to calculate that. But here are the various values, various parts that you can use to see that. And we've got these, and this works. This is how the bike actually works. Take care and have a good day. Now we're moving to chapter 10. Number 1, I'm going to let you look up. And number 2, I'm going to let you look up. Number 3 is kind of important in the sense that I want you to understand the idea of why an input is important, or why one-shots are important. So here's my input. Here's my original input. Here's the 1 second delay bit. So that would be my first one shot. That would be my first one shot right there. My next one shot that would be 1 scan delayed would be this one, X, and let's call this X1, and that would be 1 scan delayed. So that would be X1. Now X1 then could be 1 scan delayed, and that would give me my signal that is 2 scans delayed, etc., etc., etc. So that gives you a little bit of an idea of how to do this. So this is my used bit that is 1 scan delayed from this bit. This turns on. This blocks this. This blocks this. This blocks this. So basically they give you that kind of a signal. And that's for both Allen Bradley and Siemens. Okay. Number 4, that is a Johnson counter. And I'm not going to go through the detail. I do it in the book, but number 4, 10.4 is a Johnson counter. Now, it's shown in the book how to build it. How to build. So I'm not going to go through that. Why would you ever do this? Well, if I have logic that I want to do a little bit on one scan, a little bit on another, a little bit on another, a little bit on another, I can divide it up, and then each of the scans does part of the load. And then it's done on a repeating basis. And you say, well, did you ever do this? Have you ever done that? Yes, I have. In other words, if I have something that has a lot of calculations to it, I divide it up. And this is one way of doing it. So You can do it with numbers. You can do it with this relays. It's up to you how you want to do it. But scan 1, scan 2, scan 3, scan 4, scan 1, scan 2, scan 3, scan 4. You can divide the logic up. Okay, so number 5. Which one is which? So the machinery one is fail-safe. So under machinery, we should say fail-safe. And under continuous process, we should say fault-tolerant. And number 6, write the code to convert an input that's 0 to 10 to a signal that is 0 to 250 gallons per minute using both Siemens and Bradley. I'm going to leave this as an exercise for you. And number 7, same thing. And number 8 is done in the lab. And number in the videos. And number 9 is done in the videos. Number 10, give a simple way to find the average scan time without writing a program. Well, today you just look in the processor's help menu, and it will show you how you can do that. Okay. Number 11, how fast can the program of Lab 10.1 be safely executed? About in a millisecond. You can actually execute and get each of those bits that quickly if you don't have any capacitance in your lines. And again, you have to work with it to see exactly how quickly you can do it. But you can do you can do each of those bits in less than a millisecond, so that you set an input on half a millisecond, in a quarter millisecond you can read it, that type of thing, if you want to. There's no reason to, because the thumb wheel switch is really a second or two of running through is fine. But if you want to do it real quick, you can, because you can set those filtering times way down. And so that would be an answer in the sub 1 millisecond area. So hopefully that answers some of your questions about chapters 9 and 10, and we'll talk to you later. Have a good day. Good morning. Today we're looking at a problem at lab at the end of chapter 10, and in the hybrid text it's at the end of chapter 10, but I have brought this lab down and it's lab chapter 9. It's the thumb wheel switch chapter, and we're going to be talking about this thumb wheel switch and how it can be programmed. So traditionally we have used HMI programming to introduce numbers into the programmable controller. But before the HMI became available, the various HMI products that we have available today in the market, this dates us back into the 60s and 70s and the 80s. We used thumb wheel switches, and thumb wheel switches were basically a switch that gathered a number from 0 to 9, and you could gang them together, and you could put them in groups of 4 or 6. And there was no decimal point, but you could imply a decimal point if you wanted to. But you basically were collecting a number, and the way that this was done was either with switches that opened to give you the number or closed that give you the number. Typically they were ones that closed to give you the number, but they also had ones that would open to give you the number. And a lot of them had diodes in them as well. Now the diodes were placed there primarily as a way of being able to use a large number of thumb wheel switches, but only one input card. So if you had true high thumb wheel switches and true high inputs, basically you had to match the two together. So if you had true high, you would turn on the 24 volts or the higher voltage, usually 24 volts, at the common, and then you would read the numbers through the 1, 2, 4, and 8 digit bit, the 1, 2, 4, and 8 bit. So you would build a number that way, and the number would come into the program controller as a number, a BCD number, and then most program controllers in that era had the ability to convert a BCD number to an integer. We don't need that anymore, and most of those instructions have kind of gone by the wayside. You might find it occasionally, but basically those are old school. But anyway, so if you had no bits turned on, your number would be a 0. If you had the 1's bit and the 2's bit, you would have a number 3. And you would see the 3 on the thermal switch, and these two switches internally would be closed. If you had a number like this, which would be the 2 and the 4 energized, but the 1 and the 8 de-energized, you would have a number 0110 or a 6. And here's another example. If we had the number 9, it would be the 1 and the 8 energized, and the 2 and the 4 de-energized. So that gives you an idea how thermal switches would have worked in the day. And again, no diodes if you only were collecting one digit, but if you had multiple digits, you needed diodes. And typically, you had to make sure the diodes were placed in the thermal switches correctly. So there was a lot of ordering properties to thermal switches, either thermal switches with diodes to the right, diodes to the left, open or closed, and then the number of digits. So you would have all these things, and you'd have to make sure that you got the order number correct. And usually you wouldn't be able to try them out until you got to the actual site you're putting these together with. And then it was kind of late, so you usually had to make sure that these were working correctly way back in the early part of the ordering and the engineering process. If they didn't, and this is one example that they didn't, I actually programmed the program backwards, which is the way that we're going to have to do it, because in order to read the program, I would have had to have changed the diodes in this thermal switch. And there's a lot of diodes, and they're real small, and they're hard to solder and unsolder. And then you'd have the mess of doing all that. So I read them backwards, and you can do the same if you are so inclined, and that's what basically this lab is about. So we have and this is an example of reading a single digit of a number as an integer, not as a BCD number, but as an integer. So basically that gives you that capability. All right, so this lab requires a student to use the thermal switches to enter a number from 0 to 9999 into an internal memory location. The number that is represented on the thermal switches, it can be changed. So we're going to show you a thermal switch in a minute. So our thermal switches have the diodes pointing to the left. To make it work with true high logic, you have to point them to the right. But they can be read as to the left if you only turn on one of these at a time. If you want, in other words, if I only turned on this line, the C would represent the position of this switch. If I turned on two of these at the same time, which switch was closed? It's 24 volts here, don't know. So basically, you're out of luck. So if you only turn on one of these at a time, you can read the C, or the common, and it will give you the status of that specific switch, the 1, 2, 4, and 8. If you just had 4 bits coming in and you turned this whole thing on here, you would be reading which one would be coming in. So you can read it all at once. Here you have to do it one at a time. Turn on the first one, read, then turn it off. Turn on the second one, read, then turn it off. Turn on the third one, read, turn it off. Turn on the fourth one, read, turn it off. That's how you do it. Now this shows a back side of a thermal switch that we have it came as a package deal, and we actually wire this in our lab, but you do not have to see or wire this one exactly like this, because it was, but this one is one that is found in our lab, and if you want to have one exactly like it, I think the company went out of business that made these, but if you want to see exactly how it's wired, it's just like these, excuse me, it's just like these with 4 digits. Now down here, I'm going to show you physically a thermal switch, And there it is. So there is a set of 4 thumb switches, and we brought the jumpers out so that you can put them on a breadboard. And if you want to buy one of these, you can buy 4 of these, and then I think there's an end plate that goes along with it as well. But if you're curious as to how to do this, you need somebody who's a good solderer, because they have to solder the diodes in. They have to solder the diodes in here. But if you want to, you can build your own. Now, if you are on a budget, an extreme budget, you can do this on a breadboard. You don't have to have a thumb switch. And all you have to do is allow for some switches, in other words, some jumpers, put some diodes in, and then put where you're going to put your 1, 2, 4, and 8. And if you are really on a budget, you can just do this times 1. If you are a little bit less crimped, you could do this times 4. Now, the bad side of this one is that if you put all the jumpers in, you're going to get a number greater than 9. So when you do have a thumb switch, it guards you against having a number going greater than, the switches do not allow you to go higher than the number 9. With this approach, if you put all the jumpers in, you're going to have a number at 15, or F, which is a hex F, and you can, in fact, get a bigger number than with 0 through 9 here. So you have to be careful, but if you jumper this correctly, and if you don't have diodes, if you don't have a bunch of diodes, use LEDs that work, they would work. Now, a question, why does this work without burning up the diodes? Well, the C here is connected to an input, and it has an input resistance, and that input resistance guards this from burning up. Usually with a diode, put 24 volts here, you have to protect this diode with a resistor, a 5K resistor or something like that, in order to keep it from burning up. In this case, there's an internal resistance at the C, which, again, blocks this from burning up, and it works quite well just the way it is. So you don't have to worry about a resistor in series or anything. You have to put a resistor here. Nope, just a jumper, and it works. Okay, so let's go back up and talk about the program just a little bit. Okay, so we have this in color, and we're going to talk about it. And each of these outputs can only be on independently. In other words, this one turns on, then turns off, then this one turns on, then turns off, then this one turns on, then turns off, then this one turns on, then turns off. And you start the whole process over again. So this sounds kind of like a bunch of timers, and it sounds like the traffic light, and that is exactly what it is. And in the middle of this timing of when you have this output on, you read the input, and that's the C. You read at the input, and when you have the blue or the ones digit on, when you read the C, you're reading the ones. When you have the next output or the orange, you're reading the twos. When you have the next output or output 2 on, in the green, you're reading the 4s. When you have the next output on, or the red, you're reading the 8s. And you put them all together, add them all together, and you have your final answer. So that's the number that you're actually reading. So how do you do that? You have to have a output that turns on and then turns back off. And then somewhere in the middle of that time delay, you have a read, and you read on a one shot, and we're going to talk about that in a minute. And then you go to the next one. So basically you have to recurring timing diagrams, and this is what that timing diagram would look like. Output turns off or turns on, then turns off. Next output turns on, then turns off. Next output turns on, turns off. Next output turns on, turns off. And in the middle of each of these, you're going to be reading that C. Okay, so how long do these have to stay on? Well, they have to stay on long enough to see a 1 if the switch is closed. And there is filtering in these inputs. You say, well, what is filtering? Well, filtering is the ability to set up a 1. How long does it take to see a 1 at these? Well, in the Siemens, it's 0.2 milliseconds for these inputs. You have to be careful, and you have to run your program slow enough that you don't have a problem with seeing a 1. So 0.2 milliseconds, 0.2 milliseconds, 0.2 milliseconds, that's fast enough. You don't have to worry. Okay, so that gives you an idea about filtering. So you just have to go 20, 30 milliseconds, read, 20 30 milliseconds, read, 20 to 30 milliseconds, read, 20 30 milliseconds, read, and then after that a little bit you change and you go to the next one. So this is a statement of basically how you would do this program. So you clear holding location, turn the output to 0, turn on output 0, wait a short time period, 20 30 milliseconds, read the 4 inputs, then turn off output 0, turn on output 1, wait a little bit, read inputs again, see which ones are on, and then turn off output 1. Then repeat for output 2 and repeat for output 3. And the last thing you do is you move the number in the holding location to a second number for display. That allows you to look at a number solid as opposed to a number that's constantly being built. And how do you do that? Well, you would work on the watch table if it was a Siemens, and you'd work on the data table if it was Allen Bradley. And I'm going to show you how to do that in a minute. We're going to build some of these programming parts, and we're going to do it with Siemens, but the same thing applies to Allen Bradley. It's the same exact programming. Okay, so let's go back here and look at this timing diagram again and make sure that you understand how this works. Output 0 turns on. You read the ones bit of the first of the ones, the tens, the hundreds, and the thousands, and you add that bit or that number with its value to a number that you're building on a one shot. Then you turn that output off, you turn on the next output, and you turn it on, and then wait a little bit, and then read the 2, the 20, the 200, the 2000. Then you turn it off, then you go to the next one, and then you go to the next one. Okay, so let's leave this for right now, and then I'll come back and I'll look at it from the point of view of the program and talk to you a little bit about the programming of this project. Take care. Okay, we're back again, and now we're looking at the PLC, the Siemens program that we previously used for the timer, and I checked the Ethernet address, and the Ethernet address is fine. And I go down a little bit further here in the under the device configuration tab, and I find digital inputs, and this is where I definitely want to make this filtering as fast as I can. I don't want a 1 to take 6.4 milliseconds to be able to see it. I want to go a little faster. So I pick, based on previous experience, I'll pick 2.2 milliseconds, and that's good enough. And that's all my inputs. That'll be all of my inputs will be 0.2 milliseconds. So I click on that, and I basically give that my setting for all of these, and now I can at least say that my inputs are going to be picking up whether they're a 1 or a 0, they're going to be picking it up rather quickly. So I go down through and just check to see if they're all changed, and let's see my digital inputs in general. There are my digital inputs. My digital inputs. Okay, so that should be it. Change these all. They all have to be changed, looks like. We only use 4 of them, so let's just go 0 through 3, but you have to change these in order to get this to work a little faster. Well, it doesn't have to be that fast, but again, you have to change it. So let's just say we changed our first 4 inputs to 0.2 milliseconds for the time that it takes to recognize a 1 or a 0. So that's, we're at least, we've gone that far. Okay, so now let's go back to program blocks, main, and look at our program. And I've already taken the timers, and I can use either 4 or 8. And I'm going to use 4 timers, and then I'm going to start over again. So there's 3 of them, and here's the other 2, but I'm going to get rid of this one. Okay, so I have 1, 2, 3 up there. I have 4 timers. Now that's sounds like, okay, B3 up here. B3. So I have timer 1, timer 2, timer 3, and timer 4. Now I'm going to have to use an elapsed time. So instead of 3 seconds here, I'm going to put it at like 1 second. So it's going to take me 4 seconds to go around this one time. So it's going to take me 4 seconds to go around the loop. I can speed this up if I want to, but let's for right now just keep it as something you can see. Okay, so the elapsed timers have to be a value now, and the reason we're going to do that is we're going to do a comparison, and about half the way through this 1 second, I'm going to do the read. So I'm going to set up the output, and then about a half a second later, I'm going to read. So on the edge, I'm going to call this timer 1 elapsed. Okay, so that's a value that we're going to put in there, and I've got to declare it as a definable tag. And I want to see it as global memory, and I want it as a as a D. So I'm going to say define that. Okay, timer 1 elapsed. So I'm not going to go over here and do that for each of these. Timer 2 elapsed. Right click, define tag. And see it jump from 2 to 6 because these take 4 bytes. So each of these is going to take 4 bytes. But that we're talking about a 32-bit integer. Timer 3 elapsed. Right click, define tag, define. And then the last one is timer 4 elapsed. Okay, so we now have 4 timers, and we have 4 elapsed time variables that we can read. So that's what we want to do. Now, if we want to, we can download this at this point in time and try it out and see if it works. But we really trust, because we've already done this once, that we are on good grounds here, and we know that this is going to work. So basically, now all we got to do is start adding our logic. So now we want to add logic that says basically what? Well, I want to set an output 0, that turns on. This would be my first timer, my first output, that would gather the ones, information. So basically, I want to be able to set that timer when timer 1 is enabled but not done. So it would be not of B0. So basically, the not of B0, this would be on when this timer is timing, not B0. I would be able to turn on an output. So let's bring this output down here, and that would be output 0. And I just type in O 0.0, and it should take, and it doesn't. So basically, I have to redefine my tag, which is an output. Oh, it's a Q. I'm sorry, Ted. Q 0.0. That gives me my discrete output. So now it says green. I don't want that. I want to rename it. I want to say the name is, instead of green, I'll just call it output 0. Okay, output 0, change, and away I go. Okay, so now I want to have an output for each of these 4. So B0 but not B1 is the time it takes for timer 2. So basically, I come down here and I say B0 but not B1 gives me output, next one, output 0 or output 1, Q 0.1. And it says yellow. I want to change that, rename that to something that means more to me, and then I'm just going to I'll call it output 1. Okay, so that would give me my next output. Okay, so now I do this for each 4 of these bits. So each 4 outputs. I have to have 4 outputs. Okay, so I do that for B1 but not B2. Whoa. I'll put, you got it, Q0.2. Change that, that has a name, and we're going to change that name to output 2. Change the name and use it again. Okay, so we're using, now we've got these three, and then the last one would be B2 but not B3. So basically B2. Okay, that would give me my final my 4 outputs. Okay, now I've got my 4 outputs going. So output Q0.3. So now if you want to test, you can. But again, I think we're pretty good solid ground. So let's just go down here and look at the next, what we're going to do next. Now in the middle of output 0, we want to be able to read. And that's where we're going to say output 0 greater than this variable here, greater than, and it's this variable right here. It's this timer 1 elapse. So I'm going to say output 0 I didn't get my name on this last one. Okay, so the name on the last one would be output 3. Okay, so output 0 and timer 1 elapse less than or greater than, it trips over a point, and it's let's say 500 milliseconds. So let's just use my comparator statements over here. Let's go over to comparator statements. Let's do the greater than, and let's say, okay, so timer 1 elapse is greater than 500. So when we trip over the halfway point of that output, in other words, we've given it 500 milliseconds to settle in, now we're going to do something else. We're going to say what? Well, we want to have this as a one-shot. So how do you do that? Okay, so basically at this point in time, we have to create an output. Create an output, call it, we've used Bs. Now let's use, I don't, doesn't matter. Let's use R's. Okay, so R, this is the read, R0. In other words, read output 0. So that's a bit defined tag. This is going to be a, not a local, this is going to be a global memory, M0.6. We're going to define that. Okay, now this is a read output 0. So right now we're going to do this. We're going to say down here, we're going to do a one-shot. Bit logic, one shot, which is down here, positive edge. Okay, so this is a positive edge. R0. Okay, now this would be R0 what? This would be the other side of it. R0, remember, R0 REM. This would be our this would be this would be the one that's a wasted bit, but we have to do it. So we've got it. Now this is going to turn on when this turns on. So this would turn on immediately when this turns on, and we would capture the information. So this turns on, boom. Now what do we do? If there is a 1 in this, okay, so if there is a 1 in that bit, we want to add 1 to it. So if I 0.0 is on, and it's at the halfway point, then we add 1 to our word. This is our val, our value that we're going to talk about here in a second. So we're going to add 1 to our val. Val plus 1 equal val. So we're going to go back up here under basic instructions, and we're going to say under basic instructions, we're going to go back, and we're going to get back to we're going to go up to math instructions. And we'll do an add. So why don't you calculate? Well, add simpler. So we're going to do an add. So we're going to add, this is going to be an int, a dent. Let's use an int. Okay, we're going to add val plus 1 to val. Okay, so val is the unknown. So we're going to define this tag, and this is going to be a not a local temp, but an global memory, an int. Define it, and there we go. So I'm going to do a little dipsy-do right here. I'm going to go down, and I'm going to do the same thing for tens. I'm going to do this. Control C, Control V. So output instead of 0 is going to be I 0.1. Oh. So let's just delete it and start over again. I 0.1. Okay, so we really want to change these names from tag 1 and tag 2 to something else, but again, I don't really care right now. I'm just going to copy paste, copy the add. This instead of val, I want to say 10. And add it back to val. And you get the idea. Put another one down here, and that should be a normally open TED. Okay, so then we do another one. This would be I, whoops. I 0.2. Copy, paste. 100. Up to 100. Okay, and then do it again. This one would be I 0.3. This would be the same thing, only at 1,000. So now we built for the ones. You have to do the same thing for the tens. Excuse me, for the 2s, the 4s, and the 8s, and you're done. Except for one last thing, and the last thing really is the most important thing at the very end. So you're going to do this same thing for the 2s, the 4s, and the 8s. And then one last thing you're going to do, and this is the most important thing, at the end you're going to do that move instruction, and then you're going to 0 out the word val. So let's find the move instruction. Move val to val 1 to val 1, and then 0 out val. I do not want a I want to get rid of that because I do not want a immediate value, and I got one right there. You do not want those. Okay, so Okay, I've got val. I do not have val 1. That's good. I want to get back to my main program. Okay, so I want to delete that out. I want to make val 1. I'm going to get rid of that val 1. So delete that out. So if you ever get them, the only way to get rid of them is to go up to the front of your program and get them out that way. And that's what I had to do. So it's sort of a process you have to go through, but you want to get rid of them. So I do not want them dirtying up my program, so I define tag, and I do not want at local temp, I want a global memory, okay? And that way I am sure that it will, shoot, I got it again. So this is watching the instructor stumble around until he gets the thing to work. I want to get rid of the val 1 because I do not want it as an immediate value. I want it as a, let's call it val 2. Okay, so let's say val 2. Oh, let's just call it val 1. That's fine. So that way it works now. So we're going to watch this in val 1. So val is the one that's collecting the information, and then we're going to watch it in val 2, and then what we have to do next is what? Move is 0 into val 1 or val. Okay, so move a 0 in it. That wipes it out. That starts us all over again. So at the end of the thing, that's not quite right. We have to when B3 turns on. Excuse me. When B3 turns on, that's when we want to do this. When B3 turns on. In other words, that one scan when that bit turns on. The reset when the B3 comes on, when we reset the whole thing. This is the reset bit right here. This is only on for one scan. When that turns on, we want to come down here and we want to do this last little piece right here. Okay, so I'm not going to compile this for you, but this should be helpful to you to get started on writing this program and getting it to work. Hopefully this is something that you will enjoy, and when you get it done, I promise you that you'll be able to see a number that's entered in as a thumb wheel, and you'll be able to see it displayed as a number inside your program controller. And in the process of doing this, you will have not mastered, but you'll at least have a good idea about how timing diagrams work. And that's the basic goal of this lab, is to understand timing diagrams. So take care and have a good day. Good morning. Today we're talking about the chapter on chapter 10 in our text, which is also the chapter 10 of our lab book, which is generating energy from a bike. And we started out with a demonstration that was basically just using light bulbs to show the energy consumed from a bicycle. And this is a voltage generator down here with a voltage regulator on top of it. And so the student or individual would pedal the bike, and the lights would turn on. We would turn them on one at a time with the switches, and we would turn on one bulb. And this is a 50 watter. Two of them would be 100, then 150, up to 250 watts. And they would get very hard. Now we'd also do it with the LED bulbs, which were 1 watt apiece, and these would be very easy to do. So the whole premise was that we would show the difference between electricity generated from the newer style light bulbs giving the same amount of light as opposed to the old style light bulbs, which were very inefficient. So that was the goal, and then we came along and automated it and put in a display, and then things went to, as they say, whatever in a handbasket, and we had to come back and we had to redo these, and so I used it as a time to maybe look at the possibility of putting in a PLC to grab the information and then display the calories used on a graph as you went up and load. In other words, as you turned on more of the switches. So this is the formula for calories. It's in 1 joule is 0.238902957619 calories. And power in watts, which is V times I, is energy in joules per unit of time, which is in seconds. So if we moved the denominator over to the other side and we said 1 second, so we'd say power times 1 second equals energy. So if I look at the power every 1 second, I would be able to convert that directly to joules, and then you can multiply that by 0.23 or divide by 0.2389, and that would give you calories. So we can talk through that, and we will do that in a few minutes. So the processor that we are using does not have dual ended inputs, and we needed dual ended analog inputs. So we had to add a second card, and that's the SM1234 analog input module, and I'll show you how to do that in a minute and physically show you how to do that. But we have to add that card and move this little slider over so that this card talks to the processor. And the way we wired it, I'll show you that in a minute as well. And also to collect the information from the unit for the bike, to find the current, you can't do that directly. You have to do it some kind of devious method, and we did do it kind of a devious method. We bought a 0.02 ohm resistor. So we looked at the difference between the voltage here and the voltage here, and it's not much, but it is enough that we can actually get a value of current. So V divided by V was IR, so V divided by 0.02 is I, and so if we take the voltage divided by 0.02, we get the amount of current flowing through from here to here. So here would be our input, here would be our output. Here in the middle is the 0.02 ohm calibrated resistor, and away we go. The other problem we had, okay, and this is the whole system, and I'll explain what this device is in a minute. So here is the display from the back. Here is this is a switching unit for Ethernet, so you can bring Ethernet in and Ethernet out, and it won't get confused. So you have one Ethernet coming in from your programming panel or your PC, one going out to the processor, one going up to the HMI unit, and everybody's happy. This is a 24-volt power supply. It's the only power supply you need, and this is your outboard analog card. So this is what you need to set this whole thing up. You need the switch, you need the power supply, you need the processor, and you need the analog input card, which we'll show you how to set up in a minute. So there were two problems. One was getting in the voltage, one was getting in the current, and the voltage has a range on that card of 0 to 10 volts. And how do you get 0 to 10 volts when your input is 0 to 12? But then it can go over 12. It can go to 14, 15 if there's spikes and that type of thing, and that's a generator sitting there. So the faster the generator is generating electricity, the higher the voltage, but there's a voltage regulator which then trims it back to 12 volts. So that's the general premise. It could be 12 or a little bit more than 12, but we don't really know. But we hope it doesn't go above 15. That was the hope, that it doesn't go above 15. So how do you get 0 to 15 volts to be 0 to 10 volts? Well, you play a trick on it. You use a voltage to current converter, and these are readily available, and the next down it shows you how to do that. But you buy something like that, and then you put a resistor across it, and you pick a resistor that gives you a value that gets you in your range. So if I say 0 to 15 over here, I put 470 ohm over here, and I get 0 to about 9 volts over here. So basically, if I get 9 volts over here, 9.4 volts, I get the number 25,989, which is equivalent to 15 volts. So if I put 15 volts in, I get the number 25,989, and that's the number you need to remember, because now I can calibrate off everything off of that number 25,989. So if I want to capture a number, I can do that and then use the 25,989 as my calibration number. So that's how I do it. And then the bike, I look at the number on the one side and the number on the other side, the plus minus the minus, and I take the difference, and that's my voltage, or that's my voltage. So what would it be? Well, if the number is 27,648, the difference, that would give me 10 volts. We're going to get down into the weeds. We're going to get down into the 0.1 volt, 0.01 volt, in that range. It's going to be very small numbers, but that's enough we can actually count current from. Okay, so that gives you a little bit of an idea. This is the voltage to current converter. This is physically what it looks like, and we have it sitting there, and here's the specifications for it. So you can buy something like this. They're not much money, and you can add it in there, and away you go. Also, the 0.02 ohm resistor is not much money. Okay, so the purpose of this lab is to calculate the power from V times I, and to calculate the joules of energy expended, then convert joules to calories and display on a graph as a student pedals the bike. The program is to be created in a timed interrupt program, and I suggest a 1.0 second interval. That makes it simple. You can go 0.1 second or whatever, but I'll just show you how to do it with 1 second. The video shows the various parameters involved. The calculations and final display is a task of the student. An aside, if a bike is not available, a high capacity DC power supply is kind of acceptable. So you can do this without a bike. The voltage dip will be rather quickly, however, because as you turn on those 50-watt bulbs, your voltage is going to dip. So you might get a couple of 50-watt bulbs, but you're not going to get more than a couple, and your voltage is going to die. So it's a good way of, if you have a power supply sitting around that's a heavy-duty power supply, you might be able to do the same as the bike. If you want to build a bike, you can build a bike. Either way, this thing works. So that's the premise for this lab, and we're going to go now to the building of the program, at least in part, and we'll start with how to recognize the inputs and where they're coming from and that type of thing. Okay, take care. Hello again. So now we're in the program with the PLC, and we want to look at it from the point of view of how do we add the various components to get this thing to run. So the first thing we want to do is we want to physically go in and add an analog input card, which we needed because we didn't have the right ability with the input card that's the analog inputs that are right up here on the base unit to be able to do what we want to do. The reason is because one of the inputs is floated. It has a plus and a minus, and these inputs up here do not allow you to do that. They tie the 0 volt or the negative side to the common, which is the M, which we can't use. So we're picking off the value across the resistor, and that's a number that we need the voltage on the plus side, the voltage on the minus side, and we can't do that with just the difference. We want the difference in the voltage between the plus and the minus side of the resistor, and that's not able to be done with this unit up here. So we have to add an analog input circuit. So we come over here under analog input, and we pick the various ones, and this is the one that we're going to use. Kind of hard to see, but this is the 13-bit analog input card. So we bring it over here, and we land it right here in this number 2 slot. So that gives us the ability to be able to talk to that card. Now, we also want to know what the various parameters are in that card. So we want to know what those addresses are. So we want to know the addresses for those 4 inputs, and we come down through here, and we look at them, and we can say, okay, now what are those addresses? And I can look at them here, and I can see them right here, and the I/O addresses start at 96, and they end at night at 103. So basically, the first one is 96 and 97. The next one is 98 and 99. The next one is 100 and 101. The final one is 102 and 103. So that gives us the I/O addressing for these four what we call channel inputs, and that we're going to address these as the first one is wired at 96. The second one is wired at 100. So we're going to look at those two addresses. One is on channel 0 and one is on channel 2. But that's how we find it. We find it through this general information right here. So that's typically of how we would look at these. Okay. Here's what I was looking for before. The addresses for those four are as follows. Under properties, under I/O tags, IW96, IW98, IW100, and IW102. So if I want to refer to that first analog input, I say IW96. If I want to the channel 1, IW98, the channel 2, IW100, the channel 3, IW102. So I'm going to use IW96 and IW100. So the other thing you need to do is you need to come over here and you need to add the programming blocks. So you click on Add a New Programming Block, and remember we're going to add an OB that's a cyclic interrupt, and we click on OB, and then we come down here and we find cyclic interrupt, and it gives us choices. We can choose the programming language, which we will choose as ladder. I would like to choose ladder, but you can choose FBD or SCL if you want. But let's choose ladder for right now, and you have to choose a time. So a time of 100 milliseconds is what is normal. But we're going to add a 0 to that. We're going to go on 1,000. So that's every 1 second this program is going to come in and respond. So basically it's going to execute every second. If you want to execute it every 100 milliseconds, that's okay. You choose. But anyway, I'm going to choose every second. So I'm going to click OK. And now it's going to come down here with a blank area like we've seen before. And now I want to be able to get in that number. And you remember we talked about those numbers before as a number from, for voltage, the number 25,989 is equal to 15 volts. So how do you do that? So let's just go through here and say, okay, so here we pick on conversion, and I go down through this list and I find the norm. So I do the norm, and that's the normalization. So that's going to take me from the min value is be 0, and the max value is going to be what? Max value is going to be 25,989, and that's my input and output value. And then I'm going to have the value would be IW96, IW96. Okay, so that's my input. This is going to be a, what type? This is going to be a int to a real. Let's just use real. So that's going to give us the type. Okay, so the output here is going to be a variable. Now this one you can use a local variable. I don't recommend it, but you can, because we're just going to pass this through immediately and get it out to the outside. So basically, you remember this number here is going to be between 0 and 1. So the number here is 0 to 25,989 equals 0 to 15, but this number here is going to be 0 to 1, which represent a number from 0 to 15. So basically, let's call this bike volts. Bike volts. Okay, so that's bike volts, and I'm going to define tag. And do you want to do a local? This is one of the few times you can, because you're just going to pass it right over to the next guy. I still like to go with global memories. So you're talking to a conservative here. I'm going to say local. Why would I do that? just because, I guess, more than anything else. But I like to do things kind of conservatively. So, but that's okay. So I'm going to take up a M word, but you can do it however you want to. Okay. So now we're going to go over and we're going to do one called scale. So we're going to do one called scale. So now we're going to take this number, bike volts. So that's bike volts. And it's going to have a minimum value of, okay, so we're talking about minimum value of 0, a maximum value of 15. And it scales that number, and then it's going to put an output here as a bike volts out. Let's just call it bike volts. Bike volts out. Okay, so that gives you an idea how to do this. That's the preferred way of doing it. So let's just, okay, so that's a dent. Now we've got bike volts out. Now that gives me a value from 0 to 15. So now when I type bike volts out, I'm looking at voltage as opposed to a raw number. So that gets me my number. The same with current. So basically now we come back and do the same thing but with current. And now I'm going to go with the same basic flow of norm and scale. And I want to say the same basic thing, but except for this one, for current, okay, so it's 27648. So for this one, int to real, and I'm going to say min is 0, and max is what? 27648. 27648. And the value is what we call IW100. And the output is bike amps. Bike amps. Okay, bike amps. Right click, define tag, local temp. Nope, I'm going to go with global memory. I'm going to be a stickler there. Okay, so that's what I'm going to do. Now I'm going to come over here and say my 0 is what? 0. My maximum is 10. And my value is bike amps. And my output is bike amps out. Okay, so right click, define tag. Okay, global memory. So define it, and now I've got my two values. So I now want to calculate bike amps real. So I've got bike amps in terms of voltage, but how do I do bike amps real? So basically I have to say, okay, so the real bike amps, okay, so bike amps, so V equals IR, if V is bike amps real, excuse me, bike amps out, and I divide by 0.02, I get amps. So let's do that. Let's divide by, let's do a divide. Go up here and do a divide. Math, divide. Oops, I got to do it over. I got to do a little thing that comes back down here. Hang on a second. Do a sprig out, then do a divide. And now I'm going to say bike amps out. Bike amps out divided by 0.02 gives what? want to do this in real. So now I can divided by 0.02. Okay, so let's just, I've got to put a variable in there for that. Divided by 0.02 gives me, let's do this with a calculate block instead. Let's see if that works. Let's do a calculate block. Okay, so bike amps out by 0.02. Well, it does the same thing. So let's go back to the divide. I'm sorry to take the time up doing this, but I was just trying to figure out the best way of doing it. So I've got to come up with a number that's variable as a 0.02. So let's do this. Bike amps out. 0.02. And my output will be called as amps. Right click, define tag, real, not a local, global memory, define tag. Okay, so now I've got that one. So now let's see if this compiles. I don't think it will because I got this little red line under there, but let's see if it does. .02 not defined, so I've got to come back and come up with a variable and then put the .02 in that variable. So I basically have to come up with a variable that loads .02 into it. So I'm just going to have to, at this point in time, accept the fact that I've got to do a move instruction. Move, very moving expression right here. Put a move into a variable called .02. Can't even do that. So okay, so let's do a divide. Let's do a div. Okay, so I'm just going to have to put a variable in there called var1, and I'm going to have to load that with a value, and that value is going to be .02. So now I have to go off to my table, my watch table, and put in the value .02 into var1, and that will get this to work. But I have to do that. So I have to remember to do that and get that done. Several ways of doing this, and I am not going to spend a lot of time on that, but this is .02. So you divide by .02 and you get amps. Okay. So now we're looking at what? We're looking at using the formulas to find V times I. So volts times amps equal power, and then power power times seconds and times 1 is equal to joules. And then if you divide by 0.23890, that gives you calories. So then as you move through this, you just keep adding the calories up. So it's a summation. Every second you add more calories, add more calories, add more calories, add more calories. And I'm going to let you finish that off and do that yourself and give you a little bit of a chance to program this. The other side of the coin is the HMI display and how to set up a graphic display, and that is covered in the ball and tube lab. We're going to talk about it in that lab, so you can go back to that lab if you want to and see if you can set up the display part of it. But I'm not going to do that in this lab because we'll just take too much time setting that up. But that's the final straw. That's the final part of this. But now that you've got this, you can do the calculations and you can do the rest of it. And let's see, give you a chance to try to do that. Take care and have a good day.